All right, let's get started. So, I don't raise your hands, but how many of you hate me after last night's assignment? After getting done with that. I have some comments I'll make about the homework assignment, and we'll chat about it. I'll answer any lingering questions you have. I'll talk about provide and what happened with that and so forth. But you made it through the first assignment. I think at this point, hopefully, those of you who are up until like 11:59 trying to scramble might realize that starting it a little earlier and getting some like good work done at the beginning of the assignment time is probably a good idea. But I will have more to say about that in a few minutes. So here's what we're going to do today. We're going to do a little Unix tip of the day, and then I'm going to talk about the homework, the one from last night, and then we're going to talk about these things called are called the big three in C++ programming. We've mentioned one of them somewhat extensively already, the destructor, not that much. The other two are these things called the copy constructor and the operator equals overload. All right, and we'll talk about what those are for a few minutes, and got lots of questions about that this morning. As I said, the class in the morning is a little quieter, so they asked lots of questions about this. So I'm sure it'll be a fruitful discussion. And then we will finally go into the next data structure that we're going to talk about called queues, which are kind of cool. And I mentioned those the other day as well. All right, any questions before we get going? All right. So here's the Unix tip of the day. Oops, here's the Unix tip of the day. Tab completion and Control-R completion. So I spent like way too many hours yesterday in the lab and helping you guys out, which is great. I'm glad you had questions and so forth. But I stared at a lot of people, and it got, not in a bad way, I got a little frustrated watching you type like period slash right? And it wasn't that, I mean, you had to type it right, but there's a faster way of doing it, which I'm going to show you. So just so if you've typed it already. So let me show you what I'm talking about. So in the I'm in my folder up here, and if I type ls, right? Let's see. There's some files called TA office hours. By the way, somebody sent me a Piazza note and said, "Hey, put your office hours online." And I went, "Oh yeah, I forgot." So my office hours are online. They're today. They're Thursdays. Wednesdays from like 4:30 to 5:30, and then Thursdays from 10:30 to 12:30. And just email me if you can't make those times. So anyway, TA office hours. So if I start typing, like let's say I want to look through the TA office hours, and I start typing less, and then I type TA tab, right? The first time it like kind of beeps at me, like what are you trying to do? Then if I hit tab again, which I just hit tab again, it tells me all the different things that start with TA, right? And that's kind of cool. And then if I go, oh, they're all TA something. So let's go TA office. Oh, there we go. I hit tab again, and it completed a lot of that for me, right? And then, oh, I know it's a TXT, so I just boom, like that. So it's actually pretty fast, right? If I wanted to, if I was going to do something like ordered dynamic array or whatever, it's not in this folder, but /or tab, if it happened to be in this file, that would complete it for me, and then I'd hit return. So it's actually really fast to do it that way. Of course, the other way to do it is if you've already typed it before, just do the up arrow key, which I'm doing right now, and that goes to all your scrolls through all your previous commands. That's nice. Okay. So no more, you don't need to actually type make and then the whole thing if you've already done it. The other cool one is this thing called Control-R completion. If you hit Control-R, which I will do now, Control-R, it gives you this little reverse I, which stands for incremental search. If I start typing, like a little while ago I grepped through the file, I searched through the file. If I start typing G, the first thing that pops up is the last command that I used to type, that I typed G with, right? And if I went back, did a backspace and typed L or something, there's the ls command. I'm not sure what else there we go. Make hello world. All I have to do is do that. It actually goes back through all your commands. Like if I have other M ones, right? It'll go back and, well, there's no other M ones that are directly there. But it'll go back and find the last command that you did, and then you just hit return and it runs it. So it's actually really fast. A lot of people, for some reason, don't know about Control-R completion, but it's particularly fast when you want to do something that you've already typed in before. Okay? Questions on that? Not that there would be, but use it. I'll make sure you do next time I come into lab and see you in there. OK. All right, so here's what we're going to do next. We're going to start talking about, well, sorry, I guess I forgot. I thought we were going to do the next thing. We're going to talk about the homework. All right, here's the deal with the homework, too. First of all, I know a lot of you guys probably hate me right now. Sorry. Homeworks are hard sometimes. There were some issues with provide. I believe at this point, Bruce has finally fixed all the provide issues, and I apologize about any concerns you had over why is my program should be working and it's not in this test and whatever. Hopefully you saw the Piazza post that said that gave you at least the correct outputs for all those tests, even though you didn't know necessarily what was being tested. But he has fixed that, and then what we're going to do is we're going to rerun all the tests on all of your code again, and then use that for the output. So if something was broken in yours, it might not be broken when we actually look at it again, because we're going to rerun the tests. And if anything was broken in then it was our fault, it won't come up again, hopefully. So anyway, that's the bottom line. The overall idea, though, is if we make some mistake, like provide is screwed up or whatever, we're not going to penalize you for it in terms of your grade. And obviously, I've said this before, if your grade comes back and you go, wait a minute, I did this and you told me I didn't, whatever, just email me and we'll fix it. Okay, it's easy enough, I hope. All right, a couple other things. So a bunch of you looked on provide, a bunch of people went on provide and said, hey, the provide script must be broken because my case and the guy sitting next to me and the woman sitting next to me, we're all the same problem, right? Well, in some cases it was all your problem, right? Like there were a lot of corner cases. And by corner case, I mean the inserting into the end of a linked list or deleting from the front of a dynamic array or whatever. Those kind of cases that if you didn't test on your own, well, they might fail our tests. So you've got to start thinking about a lot of these tests that you're going to do and start thinking about those corner cases so that when you get to testing your own code, you can write those little test cases and say, and then see if your program actually passes those. Now, will you always get all the test cases we're going to try? No, probably not, but you should try to do as many as you can. And writing test cases is not the easiest thing in the world. I mean, it takes a little time to get up to speed to writing it, but hopefully you've got some examples in the main CPP that we had for this assignment. Here's the other thing. Look, I understand debugging is hard, right? I've been programming for, I don't even want to admit it, over 20 years, right? And debugging still is hard for me, right? I mean, it's just one of those things that you've got to, it takes time to look through the thing, and especially when you've got it in your mind what you think you did, and then you glance over something and then don't realize that, oh, that's where the problem was because you thought it was right, right? So I understand that, and that's why starting these things earlier so you have more time to debug is important. I mean, I think debugging takes up sometimes 80 to 90% of your actual coding time, right? I mean, designing the algorithm is not particularly hard. It's the getting it to work right, which some people love. If you hate it, maybe this will be your last course in CS. I don't know, but if you love it, great. I mean, I like it. It's kind of fun when it does work, right? I mean, that's nice. But here's my kind of bottom line tip on this. First of all, you've got a bug, you're seg faulting, whatever. If you can narrow it down, great. And once you do narrow it down to some little section, let's say, stop and just kind of create your thought pattern for what you're trying to do, right? If it's a linked list, draw three nodes, hook them all together, and then say, I'm going to insert in the middle, then I'm going to insert at the beginning, then I'm going to delete, and walk through that process before you even go back and look at your code. So it's kind of fresh. Then go back and slowly look through each line of your code. And I know it's like your eyes start to bleed after a while. I mean, I get it, right? It's tough to do that for many, many hours at a time. Take breaks, do stretches, whatever. But the point is you have to be very conscious of going slowly through the code and say, is this doing exactly what I want for this particular case? And eventually you'll find those bugs. And some of you, unfortunately, didn't find some of those bugs. But that's a learning time, right? Questions on that? On comments on debugging or anything else? No? OK. I also learned that Tufts students get sick a lot. Because I got a ton of emails saying, I was sick last weekend, can I have an extension, and blah, blah. And again, I've said this before, if you have a mitigating circumstance like, oh, I was sick, then email me and you can probably have an extension if there's some circumstance like that. So I'm flexible that way. But if you're sick before, like if you're sick like the week before every assignment, then I'm going to suggest you go to the doctor. All right. That's about all I have to say about homework 2. You guys have any other comments or questions about it? Yes.
Did you go over your lateness penalty?
Yeah, well, so that's the thing. I mean, my lateness penalty is, did you email me? Right? I mean, if you're not gonna, here's what I don't want you to do. I don't want you to get to 11:59 and have broken code and just go, I can't do it, provide, and be done with it. Although that's, in some cases, probably a good idea, because what's the point of like after midnight trying to code if you've been doing it for 8 hours, right? But if you get to a point where you are going to be late, email me and let me know. I would rather know that you're going to be late, or that you've got some other, that something came up or you just didn't figure it out. Because I know it can take hours and hours to debug stuff, right? That's better than either just providing it and hoping for the best, or providing or not providing until later, and then I wonder why you didn't ask me if you could have an extension. See, does that make sense? So I don't really have, I don't want to go down this strict route of, if it's a day late, it's 10% off. There's too much paperwork in some sense. And I think there's cases where it really, I don't mind making those decisions relatively quickly about if you can, should have an extension or not. Does that answer your question in kind of a roundabout way? Okay, yeah.
So I provided last night around like 11:55.
Uh-huh. You provided 11:55, yeah?
I got the error message saying, please SSH to the homework service.
Okay,
Why would I need to do that if I'm in?
Well, okay. So good question. So the question is, hey, I'm in Halligan in the lab, and I did provide, and then it gave me an error and said I must SSH to the homework server. The reason we want to do that is 2 reasons. Number 1, it's easier to check if you're on one machine than whether you're on 40 different machines, because only some of them have the right compiler that we need. The homework one definitely does. So that's really that's probably the biggest reason. The other reason is we know that one has the updated compiler, and it might not be on every lab computer. So that's it. But you ended up doing it though, right? If you were a couple minutes late, that's fine. Don't worry about that. Yeah. Please don't stress over a few minutes here and there. Yeah. All right. Anything else? Good questions. No? Yes, Lydia.
If you don't have time to answer this, it's okay. But like, what was the flood test doing?
Oh yeah. What was the flood test doing? Did anybody have an idea what it was doing? Yeah. Phil. Yeah, not only a bunch, like 28,000, I think. Random events, yeah.
When you were running flood, were you also inputting events at the same start time?
Yeah, there were some which were inputting at the same start time, yes. Yep. I didn't look at the exact code for the flood one, but that's Bruce told me what it was doing, and by the way, Bruce will make some mistakes on some of the provide things like he did, but you don't understand how good he is. Like some of these tests are tricky tests to get right to that one corner case, or the case of doing a flood where you get 27,000 of the same input, right? Your program has to be able to handle that in some way, correctly, right? So that was it. So anyway, to answer your question, it was putting in like 28,000 random events into the day, and then removing them randomly as well. So for those of you that, and I talked to some people, trying to look if you're here, I talked to a couple people here yesterday who like went through their linked list multiple times to try to get to like find, instead of keeping a previous node or something like that, they would just be like, I'll go find it again, right? Well, when you try to do that 28,000 times for things, that's why some of your programs like took more than 3 minutes and then just stopped, like it crashed, right? So cases like that, try to really stress out your program. Who knows how it's going to be used? I mean, you can, any input that is reasonable is an input that you should kind of expect. You're not going to test every corner case, but you should be able to test most of them. My advisor in grad school, she used to teach a compilers class, and part of compiling is obviously reading in the program file. And one of her test cases for what she did was all the students would submit their code, and then they would all submit various test cases, and anybody who passed all the different test cases like won some competition she was doing, right? Well, her test case for all the students was something like 25 megabytes worth of a comment, right? So it was just like one comment. They started the comment, and then 25 megabytes later the comment ended, and then the rest of the program happened. And like 85% of the students failed on that because they just didn't think to read. They didn't figure out how to ignore the comment properly. So things like that. I mean, we will only be tricky in the sense that if it's allowed to be input, we'll try it if we can. You know what I mean? Yeah. Other questions? Don't stress about it though. I mean, for what it's worth. Yeah.
I was getting these like really weird abort errors when I changed my initial capacity to 1 to test if expand was working, the expand part of my function.
Okay.
So
You're getting abort issues when you change your capacity to initial capacity to 1. Okay.
So I was able to fix that when I took out the delete in my expand, like to free up memory of the old array that I was replacing.
Oh yeah. Well. Okay. Go ahead.
When I took that out, it was working.
It was working fine?
But then I am kind of wasting memory, I guess. But do you know why that was happening?
Yeah, I don't off the top of my head know why it was happening. It could have been that because you actually didn't have any. Well, if you did have an initial one element, one event array, it should have worked fine. I mean, everything else is the same. But it might have been that it had 0, and you're trying to put something in there that didn't. It might have been a corner case, the same thing. But I'm glad it worked eventually, though.
Yeah.
Okay. Yeah.
In the file gave us the main of the computer, there was an interesting part where it included only included data as an array.
Yeah. It's funny. You're the only person that's mentioned that to me, instead of the other one. Yeah, good question. So I noticed this. I probably should have. I probably should have put some preprocessor directive to check between the two. As it turns out, because the interface was exactly the same for both the dynamic array and the linked list, it didn't matter which .h file you actually included because they were similar enough. One might have had like the dynamic array one said that it was going to have a linked list, but didn't, or I mean, sorry, an array, but it didn't. So, but it actually didn't matter in terms of the actual running. So that was a good question. Only one. Did anybody else notice that? I don't know. Yeah, it was a tricky. I happened to notice it like late this week. So. There was if you look in the main.cpp, it only includes the dynamic array .h file, not the other one. But it turns out it doesn't matter because the interface is the same. So yeah.
If you had different private functions, like so if the header files were different, but the interface that was actually used is the same, would that give you any errors? It
shouldn't. No. The question was, would you get errors if your interface was, or if your private members were different, even your public ones? C++ is nice enough that if you don't declare, or if you declare that you're going to have a function, and then never actually write it or use it, it won't care. It won't give you a warning. It might give you a warning somewhere, but probably not with our tests. All right. Good questions. Anybody else? Yes.
Are you supposed to do anything if you try to cancel an event that's not there?
Yeah. If you try to cancel an event that's not there, you should just return, because it's not there, and you just return. If you did say assert not there or something like that, I probably wouldn't take points off because I didn't explain that in the document. I don't think. But yeah. So if you had an error message and said that event doesn't work, I would not take points off for that. Anything else? OK, good. All right. I'll probably have another homework assignment. Well, it won't be Monday. Well, I could give it out Monday, but we don't have class next Monday, right? Next week we have class Wednesday, Thursday here for some reason. Anyway. All right. Here we go. This is what we call the big three. OK, this is like the C++ heavy day, a half day of the course, right? Here's what we're going to talk about. We're going to talk about this thing called a destructor. We're going to talk about this thing called a copy constructor. And we are going to talk about this thing called an operator equals overload. What we're doing is we're in the operator equals thing is we're actually saying, hey, make equals mean something else besides just equals, like you might think it stands for. OK? So these are the three things. And we'll go into good detail about this in a couple minutes here. All right. So we've talked about destructors before. Destructors simply clean up your resources. If you use the new keyword for something, you almost always need a destructor somewhere. Okay? Not always, but most of the time, if you use new anywhere, you should probably be thinking, oh, I'm going to need my own destructor. By the way, the C++ compiler, if you don't build a destructor, it builds one for you. It builds one that just returns. It doesn't actually do anything. It might not be correct, but it builds one for you. It also builds the other two methods as well. So the destructor, I think we've talked a little bit about that. You just delete whatever you've used when the class ends. the copy constructor does the following. It creates a new copy of a class and then copies the old one into the new one. Okay? Let me give you a little example of what I'm talking about. Let's say that you had int a, and then actually we'll do this. We'll say int a equals 2, and then we'll say int b. Right? If I say b equals a, right? Don't you get a copy of a into b? Right? That's what you get, right? Well, that's what these two methods are actually doing. They are creating the copies, but they're creating the copies for your class, not for primitive values like integers. Okay? We'll go and I'll draw some more things to explain that in a little bit. The operator equals is the part that says, hey, equals means something different for your class than just copy. Like it means something a little bit different. Okay? We'll get into the details of that here in a sec. Okay? All right. We're going to take a look at a little bit of code here. Okay? And hopefully this will show you what the issue is and why we even care about these things at all. Okay. So I've created a class here, and it's definitely scrunched up on the screen, so I apologize about that, but I had to fit it all on. And the class is just, it's a stupid class. It's called int cell, and all it does is it stores an integer. Right? We already know how to do that, but this is a class that's hopefully illuminating in that sense. It stores an integer, okay? And this is actually the constructor for it. What this means is it says, if you give me an initial value of 0 when you do the constructing, I will place 0 as that value. Okay, that's all that part's doing. And then it says, okay, this thing called stored value, which is a pointer to an integer, but it's in the private section. It's a pointer to the integer, an integer. It says stored value equals new int, whatever that initial value was. Okay, so if I do int cell 3, right? Well, actually, let me do it this way. If I do int cell a equals, no, I'll do it this way. Sorry, I'll do it this way. Int cell a of 3, right? That creates a variable a, which is a class called int cell, and it puts the value 3 into the stored value part of that class. So far, so good? It's pretty simple. I mean, pretty straightforward in that sense. OK, so that's all that does. We've also got a getter and a setter, which just basically returns the stored value and sets the stored value to some other value. OK? All right. The stored value is a pointer to an integer. And remember, when you have a pointer, all that's saying is, I'm going to point to some place in memory that stores something. It doesn't do the storing, right? So if you have in this case, what you've got is some area in memory that has a 3 in it, and a actually points to it, right? Well, I should say a doesn't point to it. A dot stored value points to it. Does that make sense? That's what the pointer does? OK. All right, so then we come down here and we go, all right, we're going to do this. We're going to create int cell a2. Well, I did 3 here. We're going to create int cell a2. Then next, and I'm sorry for space-wise, I went this way. We're going to create int cell b of a. And what does this mean? This means use the default copy constructor, and it says make a new variable b that's an int cell class, and make it equal to a. That's all it's doing. It's saying now b has the same value as a. Okay, whatever stored value of a has is now what b has as a stored value. So far, so good? Okay. Then we come over here and we say int cell c. And that just declares an int cell that's the c variable. It has no parameter on it, but it actually calls this constructor, and there's no initial value, so it gives it a 0. So now c has a value that points to a memory location that has 0 in it. Okay? Everybody kind of with me what's going on? Pretty straightforward, I hope. Stop me if you don't get it. Okay, that's what we do there, that's what we do there. And then we say C equals B, right? So what we're saying is B, or C gets B, right? C is now equal to B in terms of, so B gets copied into C. Okay? And then we set the value of A to 4. Okay? So let's think about what should be going on here. And then we set the value of A to 4, and then we're going to print it out. Before we print it out, let's think about what's going on here. We've created A, it's got a value of 2. Okay, so now it's going to be like this. It's going to be 2. Okay? And then B, we've said create B such that it's a copy of A. Right? Then we say C is its own copy with 0. But then we say, all right, make C equal to B. So then so C now gets what B is pointing to. Okay? And then we set A to 4. So what should print out when we do this? If we were, you can think it all through, or you can just say, hey, look, I'm saying A is 2, and then B is A, B gets A, and then C gets B. What should, and then A gets 4. So what should print out? Any ideas? 4, 4, 4. That's what does print out, but that's not what should print out. I suppose that's a technical issue. But what we might expect to print out if we did this, without knowing anything about copy constructors, you would hope that A would be 2 first off. B would be A, would get what A is pointing to. And then when you change A, hopefully you don't change B. That's not what you want. That's not what we want to do. Let me put it that way. That is what actually is happening, but not what we want to do. Okay, does everybody get what Dylan and I are talking about? That what actually prints out, Dylan's absolutely correct, is 4, 4, 4. Not 2 and then 4, 4, which I would hope that would be what printed out. Let me show you what is actually going on here. So A, stored value, points to 2. Oh, sorry, go ahead.
Why wouldn't we expect it to be 4, 2, 2?
Yeah, right. I would have expected that.
Oh,
right? Yeah. No. I would have expected it to be 4, 2, 2 because I would have thought, hey, look, I'm just creating it's a copy of B, etc. Right? Okay. So here's what's really going on under the covers. And it's this pointer that's the problem. That's really the issue here, right? So right now we say, OK, look, A is pointing to this thing called 2. When you do this, this tells the default copy constructor, which says, hey, copy A into B, copies all of A's values into the equivalent values in B. So because stored value is a pointer, B now gets its stored value, right, that points to there. It's not a different, the only thing that gets copied is the stored value, right? When you say, so C starts out like this. There's a 0 here. C dot stored value points here, right? C dot stored value points to a 0 at the beginning. I mean, right when you declare it. Then you say C equals B, and now this actually gets dropped off and gets a memory leak, actually. C stored value ends up pointing over to there. Yes?
Does it get B or does it get what B points to?
Well, it depends. Let's think about what it means. It says, well, it gets, when you say equals to a class, all you can do is you can say, oh, I'd better copy everything in that class over to the other object. That's what's happening. Okay? To say that it gets B, I mean, what does B mean? B is this whole thing. It is a int cell. All right? It is not, this is not, by the way, is this a pointer? See? It is not a pointer. If it was a pointer, then it might point to what B points to. But in this case, it gets its stored value, gets what B's stored value is. That's what's happening. Bear with us. Bear with me on this. So now we get what's going on here. When I go and change A's value to 4, what I'm doing is changing that one value right there. And that changed C's value, and it also changed B value. It doesn't change where this is located. This is located in memory. It changes what it's pointing. It changes the value that it's pointing to. They all happen to be pointing to the same place, but the value there changes. Get it? That's the tricky part, or the part where this is not what we would generally hope happens, at least except for a deal. Yeah?
So why are we able to put the incel into, so we have the incel constructor, right? We call it for B, and when
Yep.
we called it for B, we put A inside of it, but A is an incel.
Yeah.
Why are we able to
Good.
use it? Because its stored value is
Yeah,
pointed to
good
B.
question. This is one constructor. There is a copy constructor which the compiler writes for you and sticks it in your code and says, if this is another int cell, use this constructor. Yeah, it's hidden, right? Which is kind of one of the scary parts of C++. They have some of these things that are hidden. OK, but we get what the problem is if we were expecting it to be 422, right? OK. Now let's look at, I know this is going to, don't be afraid. Most of this is like the same, but I had to actually write the copy constructor in this operator overload thing. OK? All right. So take a look at what's going on here. And in fact, maybe I'll put the board up a little. Well, we'll see when we get to it. I'll probably redraw it in a sec. OK. Same thing. Nothing has changed here. This is the same first line, except now it's called int cell fixed. OK? Here is this new copy constructor. What it does is we're building it, and what it says is, OK, forget about this for 1 second, the const. It says, give me another int cell fixed class. In fact, give me a reference to one, which is we talked about that the other day. Give me a reference to that class, which means I can get at its stuff. All right? And then it says, all right, stored value is a new integer, because I'm creating B. This is like if I do this one right here. This is what's going on. I'm creating B, excuse me, and pardon me. And I'm creating the value, a place for it, and then I'm setting the value of my stored value down here to be equal to what's stored on the other one, its stored value. So in other words, I'm copying the value, not the address, not where it's pointing to. Okay? Let me put this up to do a little picture, because I know it's definitely illuminating when you get a picture of this. Okay? That's good. I'll do this. Whoops. There. Here's what's going on. This was A. Okay? And A had a stored value pointer, which pointed off to something that said, say, 2. Right? Does that make sense? This is a class A. It's got a stored value, and it points to something. We'll say it's 2. When you say B A like that, int cell fixed B A like that, what you're doing is first, you are creating some other space. Okay? You're creating some other like class instantiation called B, which has its own stored value, right? And it creates that then, sorry, right? Oh, I don't have it up there. It then creates the place for this. It creates a new piece of memory, or gets a new piece of memory, right, for itself. It's got a new piece of memory for itself. And then it says, whatever this one's value is, 2, make this one's value 2. Now, when we go and change A's later, is it going to change B's? No. And that's the whole point of this. OK? That's the whole point of that. Questions on that before I put the board down? Yes? Okay.
So is the star the same as the ampersand?
Well, no. The star is not the same as the ampersand. They're related. The star says, well, let me go to the next one where we had it here, where I say star stored value equals star right-hand side stored value. What that's saying is the star SV means go to the place where that's pointing and get ready to put something there. It's pointing here. And what's it going to put there? It's going to put what this thing is pointing, what the value of this thing is pointing at. It's called dereferencing it, and that's what it's doing. OK? Anything else on that? Okay, so, all right, well actually, I can probably leave it up here for now because I'll draw another diagram in a second. Okay, so that's what the copy constructor does. The equals operator, this is really funky syntax. Oh, I should talk about what const means. You'll see this const everywhere. You have to put that in for your copy constructor. That's the law. What that means is that you can't change anything over here. So you've actually got access to like A's value 2 there. This const says, I promise I won't try to change that 2. I'll read it and I'll look at it and I'll do it, I'll be able to like get the value, but I won't change it. And the only promise, like the compiler makes you keep your promise. Because if down here you tried to say something like right-hand side stored value equals 7, the compiler would say, no, 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 you can't do that. It's a constant value. Okay, so it's just a promise to the compiler that you won't touch it. You won't actually change it. You can see it, no touching. Yeah?
So you just make the compiler without the const?
You cannot. You cannot make the copy constructor without the const because that is the signature for the copy constructor. If you tried to, you'd probably do it, but then you wouldn't get a copy constructor. You get another constructor, and the compiler would probably complain, and it would say, I don't think I like that. It might not, but you can't. If you're going to do a copy constructor, make sure that const is in there, and make sure you have a reference right there as well. Okay? Technical details, C++, blah blah blah. Sorry. Okay. This operator equals 1. This is redefining equals. Okay? Redefining equals to now say equals, instead of being just copy, it means this. It means this whole business here. Okay? And let's look at what this means, or what this says. First, it says if this. Oh man, we haven't seen the this keyword before, I don't think. Right? This says the object that I am, that's me. That's what it's saying. So in this case, I should stop using the word this when I'm trying to describe what it means. Here, we have B equals A. This refers to B, because B equals A, and this refers to the thing that you are trying to create or trying to change. Does that make sense? But the question is, why do we even do this? What we're saying is this equal to the right-hand side? Is B equal to A? Could you say something like this? B equals B, semicolon. Could you say that? You probably wouldn't really ever want to, although there might be some loops and things when you loop through. It's easier to just do that and let it try to do it than to try to come up with the logic to avoid doing that. So there are cases where you do that. This is just saying, if B equals B, forget about it. Just return. Like, don't even do anything. We're already good to go. That's all that's saying. So that's what that's saying. Then this is saying the stored value. What's the stored value of B? And by the way, B already has to exist. In fact, down here we use C. When we get to it down here, we use C. Remember how we created C first? Remember how we created C? This is exactly the same in the bottom as we did before. See how we created C first, then later we said C equals B? C already has a place to put a value, right? So when we do this and say stored value, which is, in this case, the C here, whoops, right here, C, stored value equals what's on the right-hand side's value, B, it's already got a place to put it. And then that puts it there, and we are good to go. So it's like this. Well, we've already got B. So when we're going to say C equals B, we're going to do this. C is already going to exist, and it's going to have some stored value that points to something out here. And then we're going to say stored value of what C points to, change its value to what B points to, what its value is. So 2 is now going to go here, and now C is pointing to its own value of 2. B is pointing to its own value of 2, and A is pointing to its own value of 2. Okay? So that's where we left off. Or that's where we didn't do it before. Yes, Allison?
I was
Sure. When you say, let's say C equals B, which one's on the right?
B.
That's the right-hand side.
So you're using it as the parameter.
Yeah. It's just a variable. I called it the right-hand side to say, oh, it's the one over here.
Oh.
Yeah, good question. That's all it is. OK. So that's what the equals operator does. We'll see why we might need it for some of our code in a little bit. All this stays the same. OK, all this stays the same. And again, we're creating A with a value of 2. Then we are properly copying A into B. Right? We're saying create a new place to store B's value, move or copy what's stored in A's value into B's value, and then we're done. And then we create C, it's got its own place to store something. And then C equals B says it's up here, whoops, right here. And it says, all right, am I saying C equals C? Nope. Store then whatever, I go to where I can store a value for C and put the value that right-hand side's pointing to, what's at where it's pointing to. That was tortured. Okay? And then, by the way, it returns itself. Why does it return itself? Can you say something like A equals B equals C? You can in C++. It actually works. How does that work? Because when you say A equals B, you get back the result. You get A back as a return value. Yes, questions?
Why do we need to have the if this statement?
Mm-hmm.
Would it just be if they are the same, wouldn't it have the same effect?
Yeah, in this case, it would. I will show you a case where that doesn't make sense. So try to get used to doing it. If you skipped it in this case, it wouldn't matter. But try to get used to it, because you'll see a case in a second where it doesn't happen. Yeah? Sure. I say C equals B. Right? When I'm in the method that's this method for C equals B, this refers to C, because that's the one I'm trying to go into, and it refers to that. Good. Yes?
Why do you use the asterisk and the dot instead of the arrow?
Why do we put the asterisk instead of and the dot? Good question. This is saying, go to where right-hand side is and give me the stored value. OK? I believe that if you had done the arrow in this case, let me see. Well, you know what? It wouldn't have actually worked, because this is a reference, not a pointer. That's the difference. Yeah. You can do this, but you can't do it for, well, actually, no, I take that back. No, I don't. This is because it's a reference. I don't believe you can actually do the arrow. It's because it's not a pointer. It's very similar, but it's not a pointer. So it's actually the actual value. It's this. Think of it as, oh, it's B. Well, how do we refer to B's stored value? With a dot, because B is not a pointer. That's why it is. Good question. Yes?
Can you just go over what the difference is between the asterisk and the ampersand?
Yeah. The difference between the asterisk and the ampersand. OK. If I had said int cell fix star right-hand side, I would have had a pointer to a int cell fixed variable. A pointer to there. I would have said I had a value, some integer that says, hey, that's where it's located.
So it's like the address of it?
It's the address of it, yep. When I say ampersand, it's kind of saying, OK, you can go find the actual one and do whatever and use it as if it was as if that was the variable you were talking about. So it's a subtle difference, but there is a difference there in that when you have the reference, you can kind of do more with it, but it also isn't just an address. I mean, it's like it saves you from worrying about like the memory of the computer and so forth. It saves it. It's just the address. Yes, the asterisk is just the address. Yep. All right. And when you define it, when you define a pointer, the asterisk says, hey, this is a pointer, so it's the address. When you say it like this is saying, go to that address and give me the value there. That's called dereferencing it. Again, it's C, being confusing. Okay. All right. So we are finally able to see what the output actually is. Now it's 422. Okay. Why? Because everybody got their own copy. So when I go and I say A is 2, then B is A. That means B has definitely got its own pointer to 2. C has its own place to store 2. When I change it, I make C's value into 2. And then I say A is 4. That does not change B and C, and that's why we get this output. And it doesn't put yay, but I thought that was important. Okay? All right. Let's look at the next example of this stuff. Okay? Times it now is 3:45, right? Okay. Remember that this hopefully won't bring back bad memories from last night. All right? The day class. Now, the nice thing about the day class was you didn't have to worry about any more than one day, correct? All you had to worry was one day. As we move forward and we do the next assignment or whatever, we'll have to worry about multiple days because it's a calendar, right? And by the way, another Unix tip of the day. I don't know if you guys knew this. Cal prints out a nice little calendar for you. I don't know what day it is. Kind of fun. You didn't know that? All right. OK, so here's what we said in day. Event pointer to an event list, int event count, int event capacity. You know it well, I'm sure. Right? If we said day star a day equals new day, check. Now we've got a new day, and it's got a pointer to an event list, an event count, event capacity. And let's say we do a whole bunch of other stuff with day, and we insert events, and we insert 20,000 events, and it doesn't crash, and whatever, right? And then we want to say, hey, let's make a copy of that day. Let's have another day so we can modify those events and not change the original, right? You might want to do that. Let's say you want to sort them differently, you want to reverse them, or you want to do something else with them, whatever, right? You want a copy of that stuff. If we do this, a day copy equals a day, what this says is, OK, go call the default constructor, or sorry, the default equals operator. And what that does is it says, OK, give me a new a day, or I've got a new a day. Actually, this one is the copy constructor. Sorry, it's a little subtle. Don't worry about the difference. It says, make me a new day, and then copy all the parts of the original into the new one. So it's going to copy the pointer to this. Then it's going to copy this number. Then it's going to copy this number. Problem? What's the problem with doing that? Yeah. Yeah. You've now got a pointer to an event list that's the same event list, in fact, in memory, the same events somewhere in memory that are now pointed to. And it's exactly like the changing the 4 to a 2 changes what the other two point at. So this is bad, bad, bad in the sense of we want to copy an actual deep copy, we call it. And we call it a deep copy because it's not just copying the event list. We want to go into we want to create a new event list and create a whole new array and then copy each individual member into it. That's called a deep copy. And that's what we want to do when we do this. In general, we want to do that anyway. Okay? Let me show you how you would do it. Here's the same thing as before. Sorry, this is actually the copy constructor that's new. This is the one you're building. Okay? Here's what it is. Same thing. Remember the const. Remember the fact we have to have a reference, right-hand side. Here's what we're doing. We're saying event count is the right-hand side event count. Check. Okay? Event capacity is the right-hand side event capacity. Check. In fact, let me see. Yeah, no, that's fine. That's fine. Right-hand side event capacity. The reason we don't have a star here now is because that's just it's not a pointer anymore. Okay? And then here's what we do to look. We have to create a new event list, a new actual array of events. That how big is it going to be? It's going to be equal to the event capacity of the one we're copying in. And then we go and do the copies. You guys know this routine, right? It's just like if you're expanding an array, you got to copy all the members over. That's all this is doing. It's saying go through all the events in the right-hand side and move them all and copy them all over to the new array that you just created. Now you've got two full copies. You've got the original and you've got the copy, and they all have their own events, and nobody needs to worry about like changing one that will change the other, despite the fact Dylan wants that to be the case. OK? Questions on that? I'll give it a sec to sink in. Oh, good, it's all sunk in. This is tricky stuff. This is the copy constructor. Let's look at the equivalent operator equals overload. And by the way, I'll put this code online. If you don't see it online, somebody email me and say, hey, put that online. I forgot to put it on. Let's look at the overload. Now, who was asking the question about why it's necessary to have that this here? I forget who it was. Or why it's necessary to check? Somebody back here, I think. Yeah, it was right there. In this case, we do actually need to do this check. Watch what happens here. OK. First thing we do in the equals is we check and see, am I saying a day equals a day? If we are, just return it. We don't care anymore. Right? We don't actually change anything. If it's not, this is what we do. Event count equals the same thing as we did before for the copying. Then we do this. Remember, in the equals part, when you do something equals something, the first one has already been created before. It's already got a event list point array. It should have its own by that point, right? And so what you're going to have to do is delete that one because you don't want it anymore. You're copying another one into it. You're saying get rid of what it had before, copy a new. So you have to delete it, and then you can do a new one and then do the copying. Okay? If we didn't say if this is equal to the right-hand side, what would happen? You would go through and say, OK, good, check. I'm copying to myself. I'm copying to myself. Oops, I'm deleting myself. Right? Bad news. You don't want to do that. That would be bad to do to yourself, especially if you're about to try to go copy all the stuff from yourself that you just deleted. OK? Not good. So that's why we make this check. And if you get used to doing it, even in the cases where you don't need it, it'll help. Question? And then question. Yeah?
But so I'm kind of confused what you're deleting here because it seems like you're deleting it.
Oh, yeah.
And then afterwards, when you say event list I gets the right-hand side of event list I, you're calling on something that you've already deleted.
Ah, good question. We did talk about this for, what was it? It wasn't 2 homeworks ago. Maybe it was. When you were doing the expand, you do exactly the same thing when you're doing the expand array. Do you remember how you delete the array itself? What you're saying is you're deleting what all the stuff that it's pointing to, not the actual value itself. Because this is a pointer. Event list is a pointer, and that's still going to remain. Like you've still got a pointer. You've just said anything it was pointing to, sweep it away. Because we don't use that anymore. Then look what we do here. Here's where we create new space for it. Event list now goes, oh, I've got this new place of memory I can use. Right? And then you copy everything over.
But like when
Okay.
you're copying things over, where are you copying them from if you've already...
You're copying from the right-hand side one. OK, let's back up one step. Back up one step. If we are back up one step. OK, so we have a day, which we did all this stuff to. It's got an event list, which is a pointer to some array. So far, so good? OK. And it's got a whole bunch of values in there. We've also got some other event list. So let's say we have other day. Right? We have other day. It's got its own event list, which has some values in it. Right? It's got some values in it, like that. This is the event list. That's actually doing the pointing. Okay? What we're trying to do is take this one and move it over so this guy has a new event list. We're trying to take this one and copy it over to this guy, right? We don't know how big this one is. But we need this one to be as big as this one. And we might know how big it is. But it's easier to just say, get rid of all this and create new memory that's this big and copy all these guys into here. So do you see why we need to delete this one first? Maybe not. Maybe I said that too fast. Remember what we're doing. We're saying other day equals a day. That's what we're saying. We say other day equals a day. Check. How are we doing that? We're using this equals operator right here that goes into this function and says, fine, copy the event count over to a day's event or other day's event count. Copy event capacity over to other day's event capacity. You better create a whole new array to copy the a day's array into the new one. Otherwise, you're going to run. You might run out of memory. You might,
So you're deleting what's in the other.
the original one that you're trying to copy into. You're copying into other day.
But event list is named the same thing in both.
Sure, it is. Because it's the same class. Yeah, this is all the same class. It's all a day, which has both have event lists. Yes.
Is there a reason we can't just overwrite instead of deleting?
Well, I was trying to get to that. You could overwrite, but let's say this was 1,000 and this was 5. Well, we're going to waste a lot of memory there. Might as well get rid of it if this one's only 5 long, right? The other reason, if this is 5 and this was 1,000, well, we couldn't overwrite it. We would still have to create a new. We would have to create something big enough to hold 1,000. Right? So we might as well just do it every time instead of trying to work through some weird tortured logic to say, oh, we could keep what we've got, but just do it, just redo the whole thing. Okay, good. Yeah?
Would there be a benefit to creating the second array as event count size instead of event capacity so you have the extra?
Yeah, that's a good question. If you want to make it an exact, you generally want to make it an exact copy. So, the idea is, let's make it an exact copy. I mean, sure, you could, if you wanted to really save a little extra space, you could say, oh, that's my method for making my capacity slower, is just copying it to something new, and then I get it shrunk. You could do that, sure. But again, it's not going to be an exact copy. That would do it. Yes?
Why is that at percentage treat a day as a day?
Why is there, this whole thing, remember when you say something like this, A equals B equals C, this returns a value that gets put in here. This returns a value that gets put in here. And this actually returns a value too. Everything returns a value. Well, it happens to be you get a reference back. That's what it is. It's just that you get a reference back. You get some value back. It's a reference to a day, which is what it is. Which is, I mean, it could be just day, but the way they write this, it always is a reference. Just the way they write it. Anything else? Whew. I know that's a lot of heavy stuff right there. Want to go into something a little more fun? And fun for us nerdy computer scientists. It's good. All right. So if you do have other questions about that, feel free to ask. But those are the big things on copy constructor, the destructor, which we kind of already talked about, and then this operator overload, which is enables you to do a deep copy as well. We will have to be doing those. I would have rather not shown them to you, but you kind of have to use them. So that's that. OK, the other day I mentioned that we're going to start talking about queues. I mentioned that our brothers and sisters from Commonwealth countries actually know what queues are in the same sense that we're going to talk about them, right? If you go to a supermarket, you stand in line, right? Well, a line is a queue. OK, Q-U-E-U-E. OK, that's what it is. The nice thing about queues, it's kind of like the next step up from stacks. Okay, it's very, very similar to a stack in that it's just a list. Just a list. But it's a list that follows the following properties. Instead of being last in, first out like a stack, put everything in and then pop everything off the stack in the reverse order, queues are first in, first out, just like a line at the supermarket. Okay, which is really cool. So you've got a whole bunch of space here in some array. And we can make this an array. We can make it an array list, whatever. Or, sorry, a linked list, whatever we want. Okay? You insert at one end, and you delete at the other end. Okay? You always insert at the back of a queue, just like at the supermarket. You don't walk in and insert yourself right at the front of the line. You'll get beat up over the head, right? And you delete from the front of the queue. Okay? Now, we're going to draw these such that the line goes that way. So think of it like cash registers over here, right? And the front of the line is going to be here. And as we go this way, at least as we start out, it's going to be to the back of the line. Okay? That's the way we're going to draw this. like this. Okay? Queues, just like stacks, have two basic operations. One is called enqueue, which means that you insert at the end of the list, right? You're going to insert at the end. And you have to give it whatever object is you're going to insert. Just like push, you have to give it the object. And then dequeue, which is not Dairy Queen, it's dequeue, deletes and returns from the beginning of the list. Okay? So if this is the beginning of the list and we dequeue, we get that value. And you get that value returned, and that's what that's how you dequeue. If you enqueue, you put a value at the end of the list. Okay? We'll go through an example of this in a couple of minutes here. All right, questions on how, like, the mechanics. The nice thing about queues is you kind of already get what they are. Stacks are a little different because they're a little weird, but queues are kind of like, okay, look, I go at the back. Everybody else from the front gets served first. Yes?
Is there like an equivalent of top?
Yes, you could do, sometimes they call it peak, or sometimes they call it, what else do they call it? I forget what they call it, but there can be an equivalent. We're not going to worry about it right now, but yeah, it's the same exact thing. You can look at the top, or you can look at the front of the queue. Okay? I suppose you could look at the back of the queue. You can build whatever you want, but if it's a queue, you definitely have these two operations at least. Okay? I just thought I lost my train of thought about something else I was going to say regarding that. No, I forget. Well, so that's how the queue works, and let's talk about how efficient it is. Oh, I know what I was going to say. If you build a queue out of a linked list, right? If you build a queue out of a linked list, what two parts of the list do you definitely want to keep a track of? The head and the tail, right? You want to keep a track of the head because you're going to be removing the events from there, and you want to keep a track of the tail because you're going to be inserting them at the tail, okay? Or the other way around, depending on how you build it. But either way, that's the idea. It's a good idea to keep both of those in that case. Okay. The efficiency of a queue is actually great because you're always inserting in the front, and you don't have to actually move anything. Or sorry, you're always inserting at the back, and you don't actually have to move anything. Okay? When you dequeue, you also don't delete anything. And I'll show you why in a couple minutes. Okay? You don't actually have to, if it's an array and you delete something, you don't have to shift everything back and forth. Okay? We'll see why in a few minutes. And part of the reason is strictly for efficiency. You want it to be a very efficient operation. What we say is that these are order 1 operations. We will get into what that means later, but just keep in mind that you'll hear that again. What it means is that it takes basically one so-called operation to do an insert or a delete. We only have to look at one value to insert or to enqueue or dequeue. We have to look at either the front or the back. That's it. Okay? So it's actually very, very fast and very efficient. Okay. So here's how you actually implement a queue with a dynamic or with an array. Forget about a dynamic array for a sec. Here's how you do it with an array. All right. We have to keep the front of the array and the back of the array. Whether it's if you're linked list, you've already got the head and the tail. If you have an array like this, you have to keep the front and keep the back. Okay? Who gets served first here? 5 does. Then 2, then 7, then 1. Okay? You also want to keep the current size. It is not strictly necessary to keep the current size, but you want to, and I'll show you why. We'll figure out why in a few minutes. Okay? If you want to enqueue an element, say element 8, okay, what you do is you increment the current size, and you increment back, and then you set the array value at back to be that value. So if it looks like this to begin with, how are we going to insert 8? We're going to say, well, we've got 4. Our current size is now going to be 5. We're going to move back here, and we're going to put 8 right there, which I think, yeah, we do, right there. Okay? Yes?
What is current size?
It's how many elements are in the array. Not the capacity. It's how many are there. How many objects are in there. Okay? All right. To dequeue an element, set the return value to the array front. In other words, as we dequeue, we say, oh, this is at the front, so we return 5. And then we move front over here. What we do not do is do anything else with 5. We don't make it 0. We don't make it disappear. We don't do any deletes. We just leave it. Because all we care about is the front of the queue and the back of the queue. Okay? Bear with me on that. Let me show you an example of how we might do this. Somebody gave me an idea or a suggestion the other day to do like kind of simpler examples. Let's do this. Let's in-queue the letters A through E in this, and then in the middle somewhere we'll dequeue some of them. Okay? We'll see how this works. Special case when there's no elements in here. Okay? If you're going to in-queue, so let's say we're going to do an in-queue of A. Right? The current size, okay, beforehand was 0. When we put A in here, we put A at the first element. Where's the front of the queue now? A. Where's the back? Oops, sorry. Where's the back of the queue? Also A. This is the front, and it's the back. Okay, they can both point there. It's the front and the back. It's the only thing there. If you're a line of 1, right, you're the front and the back. The current size now is 1. Okay? All right, let's in-queue B. In-queue B. What do we do to in-queue? We say move back over 1. Back is now here. We then say the current size is now going to be 2. And we put that value where back is pointing to. So far, so good? Let's in-queue C. In-queue C. Move back over. Back. Counter's now 3. And we put C right in there. Let's do a dequeue. What value do we put in there? None. We don't know what it is yet. We're going to get it back. How do we do a dequeue? We look at the front and we say, hey, we grab the value A and we say, all right, now we're returning A. And then we move front over to here. Done. How do we in-queue? Let's say we want to in-queue D. Same thing. Move back over. Back points here. We put D in there. We make this. Oh, sorry, we forgot to make that 2 before. And now it's going to be back up to 3. Okay. Everybody get what's going on here? Yes. Yeah. What is the problem with this? You're kind of getting right to the problem with this, right? I've deleted this one, and I'm not using that one anymore. And now I'm here. And then if I add one, it's going to go here. What if I in-queued E and then tried to in-queue F? What happens? Seg faults or whatever, right? Or you'd have to do something where you're making a nice, expanding your dynamic array. But if we dequeued all these things, let's say we dequeued all this, and all of a sudden the front, let's say the back ends up over here, and the front ends up here. Right? Well, all this space is now wasted, right? Right? And you don't get it back in this sense. There is a good way to handle this, though. Here's how you do it. The problem is that you get all the way to the end and you run out of space. And you've got extra stuff here that you're not using anymore, and it's just wasting space. So what do? Yep, I see a couple people saying it. Okay? Queues, by the way, stay small. Here's what you do. When the front or back gets to the end, wrap it around to the beginning. And just say, let's say we in-queued here. OK, well, we're not going to put the 4 over here because there's no space. Let's put some other value, let's say 5 over here. We're going to put it here. Right? And you just have to do the math, which gets a little tricky, but it's not that hard, to figure out where in that thing you are. It's actually kind of fun. It's modular math. Okay? Here's what I'm going to do. Yes?
Why are we doing this instead of deleting the element?
Because it takes a long time to delete. I mean, if you have a queue of a million things long, you don't want to delete every time you dequeue or enqueue or dequeue. You just don't want to. It takes too much time.
Deleting, can we just replace the values then? Because these aren't
Yeah.
actually empty boxes. These are old.
Right, they might be old values. Yeah, sure.
We can just replace
We're just replace them. Yep, absolutely. Question. That was what it was? Yep, exactly. We're just going to replace them. They're still there, but they're useless to us. All right? Okay, yeah. Let's find out. Okay, I tell you what, give me 2 minutes and you'll find out. Here's what I'm going to do here. I'm going to put steps here, and then the previous step is going to go above it. So don't think like, oh, I just, you're mixed up. So step 1 is what it starts out at. 2 and 4, front is here, back is here, the size is 2. Everybody on the same page? Okay. So that was this step here. Now we're going to do this. We're going to enqueue 1. Okay, we were here, so you move back to the front, and you put a 1 there, and now back is here, front is here, and there are 3 in the queue. Good? All right. After the next step, this was the first step we just did, then we're going to enqueue 3. Move back over 1, put 3 here, and increase our size to 4. Check. All right. Step 4, we just did this one. Step 4, dequeue. All right. So we're going to move. We're going to return 2, and then we're going to move front to here. So front ends up here, back is in the same place, and the count is now 3 because there's only 3 there. There's 1, 2, 3. Next step, dequeue again. We were over here. Well, if we're going to be over there, we're going to return 4, and then you better move front over to here. So front's not going to point here, and there's now 2 elements in the array. Now we're getting to what you were just asking about. Okay. Guess what? If you dequeue again, you were here, you're going to return 1, and then you're going to move front to here. And front and back are both pointing at the same place. There's one thing in the queue. It's the only one. You are the front and the back. Good? What if we dequeued that one? Can you if you're the only person in a line, you don't have to stay there until somebody else comes around. Right? You can get handled too. What do? You take front, you return that value, 3, and then you move front over here. Now front's here, and back is here, and this count is 0. Question?
But if you've gone around a few times, front is actually pointing to a value.
Sure, could be pointing to a value.
So the only way you know that value is not actually front is because your current size is 0.
That's why you keep current size. Yeah, exactly.
Forget that and accidentally call something as in front.
Sure, you could. If you don't check that current size is 0, yeah, you'll be in trouble. Now, some people like to be tricky. And they say, hey, it looks to me like whenever back is 1 less than front, there's no values in the queue.
You just cycle twice. You went around all the way again, right?
It doesn't matter. If back is 1 less than front, there are going to be no values in the queue. Yep. Oh no? I bet it is. You tell me how are you going to get there if you are going back, if you are inserting at the back. So what you're trying to tell me is you are going to go all the way around and come back here, and then back is going to point there, and front is going to point there. I don't think you'd actually get there. Yeah, you'd actually wouldn't quite work out the way you're thinking. You would have to jump over front somehow before you do that. Yeah. Okay, you'd have to because front should always start behind it, and then when you get back to it, if you're 1 before it, you've got no values in the queue. Now look, bottom line on that, you can ask questions about that all day. Don't do that way. There's lots of tricky cases there. There are some corner cases where that might actually be the case, right? It might be some certain cases. So the better thing to do is just what Margaret was saying. Look, hey, look, size is 0. We know there's no values in the queue. Okay? Yeah, Margaret.
So if my queue is somewhere in the middle, if my front is actually somewhere in the middle of the array, and the rest up to the back of my array is full, but I need to add another element, I add it to the front of the array.
You do, yeah. Yeah. You add it to you add it wherever back, next, whatever the one more than back is. Yeah. Yeah, good. Okay. We're actually done. I've got a couple other things, little things on queues, but I will let you go today. We'll see you next Wednesday, I guess. All right. See you guys later.